Yeah, welcome back to another sunny day in 837 here. Start the usual list of announcements. Let's see here. So your last assignment was due last week. The next one's due. What is today? Is today Tuesday? So 2 weeks from tomorrow is when your next assignment is due. And apparently your midterm is next week. Okay. So a week from Thursday. So we're going to post the previous couple exams. The last 2 exams are from courses I taught, so if that somehow figures into your calculation of like how exams are written in this course, those will be the ones I would look at closely, although we can try to find some more ones too, just so you're somewhere. Practice material. I mean, obviously, so a question you always get every year is like, will the exam cover X? The exam will cover any material up to and including Tuesday's lecture. Yeah? What that means is if there are questions on the example midterms that involve material that we haven't covered yet, obviously you're not responsible for it. Okay? I get that email every year. Are there any questions about that logistical stuff? Cool. The other thing is, once again, your project proposals are due at more or less the same time. You can't say you weren't worried about that. Okay, so those are our main announcements. Two other small things. On Thursday, I will be out of town, so Ed will give lecture again, and I think that's the last time that'll happen, and then you're stuck with my bad lecturing for the rest of the semester. So, as with the last time he gave a talk, that won't be filmed, so you guys should show up and get on the material in person. It'll be a continuation of our discussion on rasterization, and it'll still be an nano quiz as long as I remember to email it to him before that happens. And of course today is election day, so go out and vote if that's relevant to you. You know, the other half of my research group that doesn't do computer graphics does political redistricting, so I have to encourage you guys to go do that. And to look up the shape of your political district. If you want to see a really weird piece of geometry, that's a great way to do it. I think the ACLU has a little web page where you put in your address and it just shows you how the boundary of your district has changed over time, which is fun to play with and pretty depressing depending on where you live. Okay, so in any event, rather than talking about legislative redistricting, today we're here to talk about rendering, which are quite different from one another. So we've kind of wrapped up our discussion of ray tracing and all the equipment that you can add to a ray tracer to accelerate it, textures, and so on. And really, our main next focus in this class are rendering algorithms that are fast. Right? I think something that a lot of you experienced on your homework assignment is that ray tracing is not a real-time graphics algorithm, at least the way that we've written it down in class. Although a lot of people in the challenge problem have studied how to make ray tracing happen at a framework. Okay, so instead, the typical algorithm that's incorporated into your graphics card is something called rasterization. And that's what we'll be talking about for the next several lectures. Cool. And this is what's implemented in OpenGL and something that you'll be playing with on your final assignment. By the way, is the last assignment up yet? Cool. So it's something you've already completed in your final assignment. Yes? Okay. Right. So remember that when we render interactively, the pipeline is quite different, right? Your computer these days, with pretty high probability, has a graphics card in it whose job in life really is to do rendering. At least that was the graphics card job in life until about 5-10 years ago, at which point we kind of learned that it's actually good for a lot of tasks. So at this point, the graphics processing unit, GPU, it's kind of a misnomer, right? The reality is a lot of computation happens there. But the basic idea, and what we'll see over the course of the next several lectures, is that basically your graphics card is like a sledgehammer that can just sit there and do the same task over and over again to different sets of numbers. Like that's its job in life. That's a different way of putting that is that your graphics card is a SIMD processor. Does anybody know what SIMD stands for? Single instruction, multiple data. Right? So for instance, like I could iterate over a long array and take as input 2 arrays and output an array of the sum of those 2 values. Right? So it's a single instruction, which is sum, applied to lots and lots of data, right? Just one element after the rest of the array. And that's the kind of thing that your GPU is really, really good at. It has little threads whose job in life is to be really boring little worker bees that all just do the same set of instructions. But on the other hand, what your graphics card is bad at are things like branching and loops and conditionals, all these things where different pixels get treated differently. Yeah? And so we're going to see that we're going to need a very different set of rendering algorithms to cope with that kind of architecture. But the payoff is really big in the sense that, well, the ray tracing code you guys wrote was extremely slow. With very little effort, we can get rasterization code to be really fast. Right? So for video games and computer-aided design, those kind of applications, that's where this is really fun. On the other hand, rasterizing images like this thing on the right, our favorite shiny spherical ball things which show up all over your assignment, is going to become really difficult because this contains secondary rays, and that it requires branching and incursion in your code. That's the kind of thing that's not so easy to do in GPU. Okay. So now I'm going to give you a totally facetious explanation of the difference between these two algorithms, and then we're going to see why these are just completely different species of stuff. So in the ray casting, I'm sorry, I have my coffee today, I'm like falling asleep. In the ray casting, ray tracing, whatever algorithm, our for loops look something like this, right? Remember that now that you guys have all implemented it on your homework, this should come as no surprise, right? The very outer loop of your code, right, all the way like in the main function, is this loop over every pixel, right? And so for every pixel, you generate an array that goes through that pixel, and you loop over maybe every triangle of your scene, and you find the one that's the closest. Yeah? And this algorithm, of course, with lots and lots of changes and ways to make it efficient and all that good stuff, is what we call ray casting. Right? Now, when we talk about GPU-based algorithms, or particular rasterization, in some sense, all we're going to do is flip the order of those two outer loops. Right? That is, what we're going to say is we're going to draw one triangle at a time, and then, inside of your triangle, highlight the pixels that are inside it. Yeah? And I would argue that for a lot of us, at least for people like me who are really bad at drawing, probably a lot of us use the second algorithm when we're on pencil and paper, right? Like maybe you go through all the objects in your scene and you draw them one at a time, right? Whereas what rasterization would do would be draw everything in my scene in this little box before I move on to the next one. Ray tracing. And so this is the basic GPU algorithm, but the same way that we started by introducing ray casting this way, but then we accelerated all kinds of clever ways. Right, in particular, I'd say we took this inner for loop and we showed that, for instance, do we have to always iterate over every triangle? No, right? You can boxes to help you out here. Well, now, unfortunately, our inner loop is something different. So those acceleration techniques are no longer relevant, and we're going to have a new set of acceleration techniques to speed up rasterization. Yeah? So, even though it's just a different order of for loops here, this difference really is kind of cosmetic, right? The real difference is the creative ways that we can speed up the algorithm on the right are quite different from the creative ways we can speed up the guy on the left. Okay? So the basic vocabulary word here is rasterization. Yeah? That's because the thing that rasterization produces is a raster image on a raster grid. Essentially, raster is a big grid of pixel colors. Yeah? And so that's where this term comes from. Yeah? And there are a lot of advantages and different advantages. There are a lot of advantages and different advantages. Also disadvantages to using this technique. And we'll begin to explore it today and continue over the next few classes. So first of all, let's talk about how much stuff needs to sit inside of your memory when you run these kinds of algorithms. Remember that your graphics card, one of the things that it has, in addition to a processor, is actually its own little dedicated piece of graphics memory. Unless you have a really complex scene, which is pretty common, right? So I have lots of really complicated shapes. This is maybe composed of splines and textures and all this crazy stuff. Do I have to keep the whole scene in memory if I do rasterization? No, right? Because I'm just drawing one object at a time. So I can load up that object, draw it, and then throw it away. Yeah? And that, in a sense, is one of the big advantages of this pipeline here. I can have really, really fast, but memory-limited graphics card memory, and have it sit right next to the processor. And because, for instance, in the extreme level, maybe I only have one triangle at a time sitting in memory, that's actually fine, right? All I need is that triangle plus the grid of pixel colors sitting there. And that's the only thing that I need, and I can have arbitrary complexity in my scene, just kind of flowing through the card. This is different from ray tracing, right? Where I need the whole scene at a time, because for any given pixel, I don't know what the first thing I'm going to run into is. Yeah? Okay. Right, so the rasterization algorithm, the basic technique is hiding inside of here is called scan conversion. A lot of these terms are going to sound dated, and that's because they totally are. Yeah? So terms like scan conversion, raster, and so on, they all come from the 60s, 70s, and 80s, when this was really had to do with the hardware of computer graphics, right? So scan conversion had to do with some of these display technologies, whether some laser or some light source that was kind of zigzagging back and forth along your pixel grid. Yeah? But the idea of scan conversion is that the basic problem that's going to sit inside of the rasterization pipeline is figuring out basically a list of the pixels that sit inside of a given triangle, right? And those are the pixels that you turn on when you render. Of course, that's not entirely true. If you render a 3D scene, then you have to deal with occlusion. And if you draw one triangle at a time, that can be kind of a tricky matter, right? Like think about if this triangle, like you know, maybe I have two triangles and one of them is kind of poking up underneath the other one. Right? Then I can't just draw one triangle on top of the other. I really have to, on a per pixel basis, figure out which guy is on top. And what we're going to cover is a piece of machinery which is pretty straightforward, called the Z-buffer, to deal with that. Okay? Yeah. So I guess I already kind of jumped the gun on this. I'm sorry I got all excited. But remember, what needs to be stored in memory in each case. So for raycasting, it's the whole scene. But in rasterization, it's no longer the case. Just one object. And so that's the really clever trick here. Now, of course, if you do your back of the envelope calculation, it's not clear which one wins when you write it in this perspective, right? Like, your image grid takes up some amount of space. Yeah? But what I'd argue is that that's kind of a fixed amount of space. Like, at the end of the day, assuming that you're going to display your image on the computer screen, there's some piece of memory somewhere which is keeping the pixel colors around. Yeah? So you really don't have a choice on that front. But what you do have a choice on is how much of your scene you keep near your processor at a given time. Beyond that, actually, even if you just do the basic back-of-the-envelope calculation, even for a relatively large, like a 1080p image, right? That's 24 megabytes of data to store. If you have, what, 64-bit color, I think it's pretty standard. One thing you'll see is it's very easy to exceed 24 megabytes in storing the geometry and textures in the scene. And so the way that we get around that in rasterization is to stream. Hopefully you guys know this term streaming, right? So the idea of streaming data is you kind of have data moving through your processor, you make use of it, you throw it away, and you move on to the next thing. And you don't have to keep it around, but as long as you use structures like the Z-buffer properly, that's perfectly fine. Okay? Right, so those are the positive aspects. That's why we like rasterization. Why do we struggle with rasterization? Well, one thing, we need primitives that are scan convertible, right? In other words, we need a basic algorithm for drawing each of the primitives that compose a shape, right? So, for instance, if I give you an ellipsoid, right, that was a very easy thing to ray trace, right? You take a sphere plus a transform. But if I asked you to give all the pixels that were in the inside of an ellipsoid on your computer screen, it's actually not super easy to do that algorithmically, right? It's kind of annoying. There's square roots involved and so on. Yeah? Lighting artifacts and shading kind of as a byproduct of the fact that typically the only thing rasterization code knows how to do is draw a triangle. Triangles have really boring shading, right? They're flat. And you often see that in basic rasterization code. And we have to go to a lot of work to counteract that and have more realistic shading and lighting models. And then finally, probably the biggest two issues are the second two bullet points here. For one thing, things like shadows and reflection, transparency are extremely hard to get right in the raster pipeline. Like for instance, one thing I want you guys to think about when we talk about rasterization today, we're going to talk about a Z-buffer, which is a really simple data structure, and it's just keeping track of the depth of the closest object you've seen so far. What do you do with a Z-buffer if you render a window? Yeah, the window's kind of shiny, and it sits on top of stuff that's behind it. So what's the depth? Is it the depth of the window? Is it the depth of the stuff behind it? What order do you render stuff so that shows up right? It's not so easy. Yeah? And that's where things get really annoying. The other issue, and a good vocabulary word to remember, is overdraw. Yeah? So the idea of overdraw is, let's say that I'm rasterizing this sphere, this polygonal shape here. Yeah? There are a lot of polygons that you can't see, right? For instance, there are these back-facing triangles that are just on the back of this object. Does the rasterization algorithm know that? No, it just draws them one at a time, and then if some other one gets drawn on top, then fine, right? And so what that means is you end up wasting a lot of work per pixel because you rasterize a whole triangle that's not even visible on the screen. Yeah? Whereas, for instance, in the ray tracing algorithm, when did that BRDF happen? Remember, we evaluated the BRDF only after I found the closest object. Then I did my shading. Here, for instance, I might do my shading for this back-facing triangle, even though I can't even see it. And so that's one potential source of complexity, especially for really crazy scenes that you rasterize. Okay. So anyway, I think this is really the big trade-off here. Right? Ray casting is easier to do these sorts of things, but it's not SIMD, and it's traditionally been too slow for interactive applications. Although all of these things change, they change year to year. Every time I teach this class, there's a race between accelerating ray tracing, accelerating rasterization. It depends mostly not on graphics people. It depends mostly on like hardware architecture and people whose job it is to make processors that are really fast. Right? Because depending on whether you make like a really good Intel chip that can just do a ton of throughput in a single thread, you know, that's useful for ray tracing. Or if you make a really good NVIDIA chip and that can do tons and tons of more simple calculations in parallel, is really the determining factor in terms of which one's faster. Okay, so that's the basic kind of high-level summary. Everybody kind of get the basic idea? Cool. All right, so let's talk about the graphics pipeline. When we talk about pipeline, we really mean like all the different steps that go into generating and rendering a scene. Right? And we've already talked about a lot of this stuff. Right? We have a geometric model. Today we'll mostly think about triangles. We have some lighting material model that's going to be hidden in a shader. And we're going to see that although shaders maybe were not super important for ray tracing, just think of them like functions that you call to say what color your pixel is. They're going to come and be extremely prominent in the rasterization pipeline. And we also had some notion of viewpoint and projection, which is going to come into play here too. And then finally our output is some color. Let's revisit each of these steps in the context of rasterization. So the first step is projection. Notice this is already different from ray tracing. Did you ever explicitly project every triangle in your scene in ray tracing onto the image plane? No, right? You made a 3D ray and you just computed color. But here you actually take the triangles in your scene and you put them onto the 2D image because that's what you want to draw at the end of the day. One fun math fact that you guys should all check at home, which is not obvious, and I think everybody assumes in graphics class but they don't think about very carefully, is if I take a camera projection of a straight line, it remains a straight line on my computer screen. You guys have to see how that's not obvious? Like the camera projection formula involves a divide, right? There's that divide homogeneous coordinate in there. Right? So you could have gotten unlucky, right? And like somehow you drew a straight line in 3D and it turned into like an arc in 2D. But thankfully that doesn't happen, right? And that basic observation, even though it's obvious and like it just involves doing a little bit of algebra, is really what's motivating this algorithm, right? Because what it means if I want to draw a triangle sitting in 3D, it's the same as like the pixels that I light up are the same as projecting the 3 vertices of that triangle onto the image plane and then rasterizing that, right? So it's enough for me to do just 2D algorithms for this scan conversion technique. Does that make sense, everybody? It's kind of a key point here. And that leads to something we'll have to talk about today, which is how do you rasterize a triangle? In other words, how do you figure out what pixels to light up, which pixels are lit when you want to draw a single triangle in your scene. Of course, you guys already have one means of doing that, right? You could iterate over every pixel in your computer screen and just check to make sure that it's on the proper side of the 3 lines that define the triangle, and that's a set of equations we worked out, what, about 3 weeks ago. Let's see, that's actually more or less what your GPU does right now, which is a little disappointing. But there are faster algorithms out there. Then, so this, in OpenGL terminology, this is the phrase you might use here is that you are generating fragments. So a fragment is roughly a pixel in your scene, but because of overdraw, there may be more fragments than there are pixels. Then after you generate your fragment, then per fragment you do some computation to actually determine the color. And this is basically the BRDF calculation we've already talked about. And then finally, you decide, and this almost seems a little backward, but in order to get rasterization to kind of work right in a parallel way, you decide whether you actually keep that value or not. And this is the data structure of the Z buffer. Right? So a buffer in general is a piece of memory that is structured like an image grid. Right? So on the one hand, there's like the video buffer or whatever, which holds on to what you're actually going to display on your screen. The big idea of the Z buffer is in addition to that, to keep a separate buffer, which you don't actually display, but it's just keeping track of depth values. And that way, as I rasterize a triangle, I also per pixel compute the depth of that fragment. And if that fragment has a bigger depth than what's currently in my Z buffer, I just throw it away. That makes sense? Cool. All right. So that's the basic rasterization pipeline. And you can see it already looks a lot different from ray tracing. Right? Most of these steps are not things that we did in ray tracing. They also more or less imitate what we're going to see happens in the OpenGL library. So in particular, OpenGL gives you access to roughly two different types of shaders that people could write. One of them is called a vertex shader, and the other is called a fragment shader. Right? And the idea is that your SIMD processor is going to have to do SIMD on two different types of data. Right? One is like messing with the vertices of your triangle mesh. Right? So that would be, for example, projecting the vertices of your mesh into the 2D camera plane. The other is parallel over pixels in your screen, and those are vertex and fragment shaders, respectively. Make sense? That's the basic abstraction. Okay, so at the end of the day, this is somehow our modern graphics pipeline for raster stuff, right? Which is for each triangle, set up all the edge equations for every pixel, see if the pixel's inside, and if the Z is visible, then render this thing. Okay. Cool. So let's do a little more details. First of all, projection. We already talked about it. It's the same projection formulas. Yeah. So this is a great thing to review before your midterm, which apparently is next week, which means I need to write a midterm, which is a good thing I asked. Right. And of course, we talked about two in this class. One is perspective. The other is orthographic. Orthographic perspective, camera projection is really easy. You just throw away the Z coordinate. Yeah. The camera projection is a little more complicated. Effectively, remember that the way the camera works, because they're kind of pinhole objects, is the farther away objects are, the more you can see. Yeah. So effectively, what you need to do is divide by Z. Yeah? And we have this handy homogeneous coordinate system for doing that, which says that if I don't like doing division, I can actually represent that point using XZZ. This is common in graphics pipeline because division is marginally more expensive than multiply. So if I can eliminate one division, great. We might as well do that. Yep. And so what you'll see in the graphics pipeline often is that they'll do a ton of different transformations, and then only the very last step do they homogenize, or I guess dehomogenize? Divide by the last coordinate and get the actual position on the screen. Right? They try to avoid doing that until the last step. Cool. And just for a little bit of review, remember that one way to do perspective is just to copy the Z coordinate to that third guy, which effectively divides out by. And the extension of 3D is the same. Okay, so there's a caveat here for rasterization, which is important. Remember that there's sort of two stages in that algorithm I mentioned, right? One of them is generating the fragments, and the other is shading them. Right, so generating the fragments, which pixels are inside of this triangle, and then shading is actually deciding what I'm going to put there. So in fragment generation, this information is all you need, right? You know the 2D positions of the points projected into the camera plane. You generate the list, and now you know the list of all the things inside of the triangle. Is that enough for shading? Like if I know the normal at the 3 vertices? The answer is actually no. So when you take, if you take a camera projection of a triangle, and I keep making this gesture, I don't know if you guys are understanding what I'm trying to communicate. If I have 3 vertices of my triangle, like 2 close to my eye and a 3rd far away, right? Then what I've argued is I can project all 3 of these guys onto the camera plane, and then compute the list of pixels that are inside of the 2D shape, and those are the same as what I had when I started. But I have to be careful when I do stuff like lighting, right? So for instance, let's say I have a light that's really close to this vertex, extremely close, right? Then it really needs the knowledge of depth to resolve the fact that there's just a small highlight near that light bulb, yeah? And so what that means is in the graphics pipeline, what changes? Remember that we talked about barycentric interpolation? What is not the same is barycentric coordinates in 2D and 3D. Does that make sense? So like if I have, let's say that my camera, I'm going to totally fail at drawing this picture, but I'm going to try. Okay, bear with me. Okay, so let's say I have a camera like that. With me so far? and here's my image plane. And here's where we're going to fail. So let's say that I have a triangle with 2 vertices that are in the image plane, and one vertex is like really far away. Yeah? It's a triangle. Yeah? So what does it actually look like in 2D? It looks like some itty-bitty triangle like that. Really, this point is far away and these 2 points are close. So the thing to be careful about is, let's say that I choose a point in the inside of the triangle. Right? So that corresponds to some point here. Yeah? There are 2 different ways that I can compute barycentric coordinates, right? One is to take this 3D triangle and do that triangle area thing we talked about, right? The other is to take this 2D triangle and do the same thing. And what I'm warning you guys is that these are not the same, right? And so what you need are what we call perspective corrected barycentric coordinates, which we'll do in the next lecture. Okay? And this is going to be a sneaky way where what we're going to do is, because we really like to do as much 2D math as we can, rather than doing rasterization in 3D, we're going to rasterize the triangle in 2D and just change the way that we compute barycentric coordinates on this guy when we texture it, so that secretly they know something about the camera projection they have. It's a sneaky trick. Okay. Right. Incidentally, one thing that people do, because we really just don't like division. Division sucks, right? Because, like, for instance, you could have your eye like right all up in the walls business, in which case you'd be like dividing by 0. And so the way that we get around that is oftentimes you'll store 1 over z in your z buffer instead of z, because it doesn't matter, that's still ordered. Yeah? And that way you can read that right off of your homogeneous coordinates without needing to divide that. Does that make sense? Cool. Here's another way that you can visualize what goes on in the z buffer. So remember this vocabulary word that we had called the view frustum? This is like that little polygon that's sitting in front of your face all the time. You might not know it while you walk around, but it is. And this is like the cone of all the stuff that you can see. Right? It's called the frustum. And it looks something like this shape that I've shown you in blue here. In a sense, what the camera projection matrix is doing is it's taking this shape and mapping it to this one. Does that make sense? And so, essentially, these are the coordinates we care about in the image plane, and the z buffer is just keeping track of that 3rd dimension of the cube. Okay? So that's just another picture that you can draw. Okay? Right. And so the image that you obtain is just by dropping the z coordinate, but you do have to be careful to keep it around the z buffer. Okay. One thing that's a little bit different from ray tracing is that typically, I mean, your view frustum in ray tracing might have been an actual cone that came out of your eye, right? Like, just goes off to infinity. Typically, in the rasterization pipeline, we'll keep track of a z min and a z max, and just say anything outside of this range of depths, I'm not going to rasterize. Do you guys think there's some reasons why I'm not going to do that? There are a few, actually. Yeah.
Far away.
What's that for you?
Like, if it's far away, it might be noise.
Yeah, if it's too far away, it's probably small. It doesn't really matter that much, but it makes a noise. So one thing you can do, remember in your streaming pipeline, right? Let's say I'm streaming one triangle into my GPU at a time, right? How many calculations does it take to check if my triangle is inside of the view frustum? Not that many, like 10, yeah? So what can I do if all 3 vertices of my triangle are outside of the view frustum? False. You can't. But you fell for mention. In particular, if I have a view frustum like that, I can draw a triangle like this, and I still have to render it. That said, you can check if a triangle is visible or not, but a little more carefully than just checking if the vertices are in the frustum or not. And if they don't intersect, then you don't have to rasterize. You don't have to generate fragments. No. So you don't even have to give it to your graphics. Yeah? And so another reason to have that z far is you could just eliminate parts of your scene that are outside of that box, and that's that much stuff less than you can render. Yeah? There's actually a 3rd reason that we like that. Let's say that I have a 3D model of all of MIT, and I'm rendering the inside of a microscope sitting inside of an office that's not mine because I'm a theorist. Yeah? What are those z values going to look like? Well, they're going to have this huge range, right? On the one hand, I'm rendering, like, I don't know, what do people look at in microscopes? Like, I don't know, cells? Like microbes, whatever it is that people do in biology. And those are on a very small scale, right? So my depth values are going to be like 10 to the minus whatever. But because I have like all of MIT around, and maybe even like the center of the Earth underneath my microscope, whatever, those depth values are going to be really large. So how many bits of precision am I going to need in my depth buffer? A lot, right? I'm going to need a lot of decimal points to keep track of that big range of numbers, right? And so one of the clever things that having the z near and the z far allows you to do is to limit the precision that you need in your depth buffer, right? A different way of putting that is like, let's say that one of my paramecium is like sitting on top of another, right? And remember my depth buffer, how am I going to check that when I rasterize them one at a time? Well, I'm going to compute the z value of paramecium 1 and check if it's closer to the z value of paramecium 2. Yeah? So I better have at least enough bits in my depth buffer to be able to distinguish between those two z's. But that means that like that regime of differences in z is quite different from the regime of distances in this room, right? And so if the z near and z far are very different, then you're going to run into a precision issue because you only got 32 bits to work with. Often fewer, it's pretty common to implement depth buffer in fixed precision arithmetic for the speed. Does that make sense? This is one of these annoying details to get right. Yeah? And oftentimes you see people get it wrong, by the way. So one thing that will happen a lot is you'll render two nearby surfaces like that. And what you'll see is the two, it looks more like that. The two surfaces kind of cut into each other. The vocabulary word for this is called z-fighting. I think it's cute. And it has to do with the fact that the bits in your depth buffer are not enough to resolve the difference in height between those two objects. And so the one on top is just kind of random. Yeah, it's your question.
Do they like dynamically adjust the z near far throughout different parts of the scene?
It depends who they is. I think some fancy graphics pipelines probably do. In computer-aided design and in animation software, it's pretty typical to just tell the artists, like, please choose the z near and z far. In a video game, you probably don't want to do that. But I think many of you guys have probably experienced video games where like you're driving your Mario Kart or whatever into a wall, and then suddenly the wall disappears a little bit when you get too close to it. And that's because it came within the z near and I think I clipped. Okay. Right. Yeah, and so this bounds the storage precision you need for depth values, which is useful. Yeah. Right. So another fancy term here, which doesn't matter a whole lot. Remember, we already talked about these normalized camera coordinates, and we think of your computer screen as the range between -1 and 1. Essentially, what the z buffer does is map z values to a range between -1 and 1 as well, but you can only do that if you have a z near and z far. Okay. By the way, in case this wasn't annoying enough, OpenGL and DirectX can't decide whether it's 0 to 1 or -1 to 1. The great thing is that in the new version of OpenGL, we remove the standard altogether, so you can choose whatever number you want. And so essentially what the latest version of OpenGL does is remove all this functionality and ask you to implement it yourself. Kind of processing for this reason, right? Because it sort of said, there's some arbitrary decision on camera projection that we were making for you, but who are we to make that decision? So they just removed it. This is great for professional graphics people, really annoying for teaching, because it means like you guys have to start from scratch, right? Like there's nothing to build from. So the actual camera projection in OpenGL, if you read, at least this is OpenGL 1.0 where they actually told you these sorts of things, notice that there's a denominator of far minus near here, which makes sense, right? Because we're trying to normalize where that range becomes the unit. Okay. Right. So that's the projection step, and this was, notice I have to say was, the OpenGL model view matrix. But in other words, it is a matrix that you keep around in memory. And essentially, what's going to happen in your graphics card is I'm streaming in all of these 3D triangles into my graphics card one at a time, or hopefully like 100,000 at a time, if you have a good graphics card. And then what will happen is it runs that vertex shader on every single one of those, right? So it has a constant matrix that it just hits onto every single one of the 3D triangles on their way into the graphics card, so that all the other steps in the pipeline don't even see the vertex triangle; they just see the results of that multiplication. And this comes from a vertex shader. In OpenGL nomenclature, let's see if I get this right. The variable, so you guys are gonna write shaders in your final assignment, and you're gonna notice. So like we're very used by now. You guys have been writing C++ code for a while. You're basically experts. Remember, there's all kinds of data types you have to be careful with in your C++ code. There's floats and ints and doubles and all that stuff. In OpenGL shaders, there's an additional piece of information. Like, it's going to look a lot like C++. There's an additional information you're going to have to put in front of those variables that is uniform or varying. Yeah, that's the keywords, I think. Did I get it right? Yeah. They change it on me all the time. I hate them. Right, so a uniform variable is one that all of the shaders see. Right, so for instance, the model view matrix, the one that goes from 3D into camera coordinates, would be one that every single thread is going to need access to at the same time, but is read only. Yeah. Whereas a varying variable might be something per vertex that every thread sees independently and no two threads get to touch at the same time. Okay, and that's going to be the basic abstraction that's going to happen a lot in GPU code. Okay. So hopefully at this point we've done like to total exhaustion, going from 3D data to 2D coordinates, and I've convinced you guys that this is the thing we can parallelize. Yeah? Any questions so far? Cool. All right, so now I have a long list of 2D coordinates on my computer screen, and my job is to rasterize them all, right? To generate fragments, which are just lists of pixels that are inside of every triangle. Of course, in reality, we don't actually generate a list. Like probably your graphics card has like some dedicated piece of memory that knows that it's associated with a pixel grid. But in concept, at least, that's what's going on. Okay, and there are all kinds of different algorithms for generating that list of fragments, and these are called scan conversion algorithms, which again is a dated term. We don't actually scan convert anymore. Yeah? If you watched old TVs, they really did, right? There was some line that would advance down. Yeah? And in fact, actually, up until a couple years ago, your cell phone camera did some version of scan conversion. Do you guys remember this? Like, you have something called a rolling shutter, where if you took video on your cell phone and you like turn around too quick, right? You're taking your selfie and you're like, I don't know how that works, but you move your camera fast, and what you would see is all of a sudden all of your objects in the scene would like shear. And the reason is that your camera had this rolling shutter where it was only really reading one line of pixel colors at a time. Right, so if you move your camera too quickly, you're kind of seeing history happen unfurl in front of your eyes. And essentially, these scan conversion algorithms are quite similar, right? They would go down row by row in the list of pixels and generate a list of pixels out of the triangle in a given row. Okay? Right, so this is this basic interface, once again, from the kind of continuous objects to the discrete world of pixel grids. And we really are making some discrete approximation. Remember something I've mentioned to you guys many times, which is that these algorithms are so easy to get wrong. And thankfully, I'm a nice guy and I'm not going to make you implement them. But they're, like, if you go work at NVIDIA and in like their basic graphics card division, the part that actually cares about graphics, which is relatively small there these days, here's the thing. Like, when you were to Ray Tracer, all of you guys, and I know because you were all my officers, were really sloppy about things like rounding and precision, right? Like, you know, if you're reflected ray is somehow reflecting what the surface just ran into, you just offset it by some magic number you made up. Would that fly at NVIDIA? No, right? Because if I'm generating fragments for two triangles that share an edge, and they really, like, honest to goodness share an edge, like they have the same two vertices that they share, I better make sure there's not a hole somewhere between them. Yeah? But think about the rasterization algorithm where your outer loop is over triangles. You draw all of the left guy and then all of the right guy. You don't get to go back and like fill in the hole that you missed, right? And so these people are so careful about making sure you generate precisely the right fragments, and doing that carefully involves like talking about rounding and precision and all that good stuff that nobody likes. Right. But so we're going to talk about it at kind of a conceptual level today. And it's just something that I can't emphasize enough how irritating it is to get this stuff right. Right, so let's talk about drawing a triangle. Of course, one thing we know is that the triangle is composed of 3 lines. And in particular, a triangle is the locus of points that are sort of underneath 3 different planes, or 3 different half spaces here. Right? So when I think of a half space, it's like all the points underneath this line. And if I give you 3 lines, then effectively I have a triangle. Okay? And so in a sense, the job of the scan conversion algorithm is to find all the points on the pixel grid that satisfy those 3 constraints. Yeah, so if I think of an edge as some line like this, right? So this is a set of all points where this is 0, and then you're inside it if this expression is like maybe positive for all three of these guys. That makes sense. This is all should be reviewed for a few lectures. Cool. All right. So what would be the world's lamest rasterization tool? Well, I could plug in the XY position of every pixel here, check its sign. And if it's positive, for all three of those guys, keep it. Then make a second pass over my image and just make a list out of all the fragments that have 3 positive numbers. That's a perfectly legitimate way to rasterize. Is this fast? No, right? I have to iterate over the whole image. Right? So in terms of complexity, what's my complexity here? Well, it's the size of my image times the number of triangles I have to rasterize. Not so great. In fact, arguably worse than even simple matrix. Okay. Okay, so that's the main problem. This is not terribly efficient. And in particular, right, if I have like a triangle which covers 1 pixel, which is a pretty common scenario, like I'm doing an awful lot of work to draw to try to get one. Okay. How can I fix that? Any ideas? What can I do? Yeah. Use a bounding box. Stellar suggestion. So for one thing, you know, obviously anything outside of the box around this triangle I don't have to rasterize. So I might as well draw this box and only apply my GPU to this little patch of memory. When does this fail? When is the worst possible triangle for this strategy? I see you're making the right hand gesture there. Yeah, if I have a long diagonal slivery triangle like this, what is the bounding box? Well, it's like the whole screen. You know, even there, it's just just a few pixels. Yeah, so that's where you can run some trouble. But in any event, yeah, that's a pretty reasonable thing to do. It's just only iterate over the pixel of a bounding box. And by the way, I think this is roughly what your graphics card does at this point, which is funny. Your graphics card is so good at parallel computing that anything more nuanced than this may actually not be worth it. Because in the time it takes to do any conditionals at all, I could have just taken the sledgehammer approach of checking it and all the pixels are inside, and that's often faster. This is depressing, right? All of us come up with these clever graphics algorithms, they don't get used anyway. But there are different ways to do better here. Yep. Can anybody think of an algorithm that would run in time proportional to the number of pixels in the inside of the triangle? This is a fun one to think of. This is what we used to do. Like 20 years ago, we spent 3 lectures developing all these algorithms. Yeah. You could do a float fill, but float fill is kind of recursive, right? And we talk about depth first search. It's probably not something to do with graphics card. So here's one clever technique. Let's think for a second not about rasterizing triangles. Those are kind of tricky. How could you rasterize a line? Well, remember we actually talked about this a little bit in ray tracing, right? I could find one point on my line, and then I could just walk either over or up, depending on the slope, to find the next pixel on the line. Like I don't have to do some big search to find it. So one really clever technique, which I think actually your graphics card may use depending on the precise chip, is like one thing you can do is find the lowest point on my triangle on the computer screen, because that's the lowest pixel I have to rasterize. Yep. And now there's 2 lines coming out of this guy that go up, right? So what I'm going to do is I'm going to rasterize those 2 lines just enough until they go up to the next row of pixels. Yeah? And then what do I know? Well, I have 2 points on the same row of pixels, and everything between those 2 points needs to get rasterized, right? And then I can take these 2 guys, walk them up 1 row of pixels, and then fill in the whole row. You guys see the clever trick here? So this is an algorithm where it's proportional, in time proportional to the number of pixels I need to light up, right? Because in every case, I just draw the outside of the triangle, so to draw it pictorially. I have a triangle. I'd start down here, and then I'd maybe march, so maybe here's like a row of pixels, right? So I would find this point and this point, which is an incremental computation I can do from this guy. And I say, well, now that I have the left and right one, now I can call my GPU and be parallel over all of these pixels on this line. And I don't have to check inside, outside at all. I know that they're all on the inside. two outer limits of my triangle. Yeah? And then I say, okay, I'm going to move up the next row of pixels. You're going to have to be a little careful because my triangle ended. Here's the next line, and then parallelize it. Right? It's a really clever technique. This is closer to what people think of as scan conversion, because you really are doing a scan line by scan. Yeah? Right. So this is this idea of incremental edge functions, and it saves you some adds and multiplies. In fact, there are all kinds of tricks. So it used to be when like your graphics card wasn't that parallel, you could like try all kinds of fun things. So one thing people might do is say, maybe I really want to say that I'm doing my graphics card, like I have a cheapo like Nokia cell phone and I want to rasterize a triangle. Well, it might be expensive for me to keep both of these two lines around. So instead, what I'm going to do is walk up and then go over, and then walk up on this line and then go back, and kind of zigzag my way through the interior of this guy. Okay? So all this is to say that there are algorithms that never leave the inside. So they run in time proportional to the number of pixels, rather than time proportional to the number of pixels in the bounding box, which could be quite different. Does that make sense? Yeah. And notice that with every one of these magic tricks I add, the algorithm becomes less parallel. Right? This is a single-threaded technique if I want to zigzag through here. Yeah? And so it's really up to the hardware architecture guys to decide whether it's useful. Right? Like for instance, it could be that this is still valuable, and that what I'm going to do is parallelize over every triangle, and I have millions of triangles in my scene. But for every one of those guys, I'm going to do this in a single effect. That would be a reasonable thing. If you're wondering, I have no idea what goes on in this, like GTX or whatever. It changes. Yeah? The great thing about these people is it's so transparent that it doesn't matter. Okay. If you like this kind of stuff, I encourage you to take a look, like for instance, at this PhD thesis I've linked in the slides here. So what these guys propose is using space-filling Hilbert curves to fill an object, which are kind of cool. I don't know if you guys have ever seen these curves before, but it's a construction that shows up in math. It's a nice way to kind of fill a volume by coloring it in one. Okay, so of course, you could ask, like let's say that I have an algorithm that's parallel enough that really I just want to compute a bounding box and figure out what's inside, and anything beyond that, all these rasterization tricks are actually slowing me down because I have more threads than I have pixels in the scan line. Yeah. Is there anything I could do that maybe would be a little better? One thing I could do is say like, okay, well, in reality, maybe I take the number of threads and I take the square root of that number. Yeah? What does that give me? That gives me the size of a box that I can render completely in parallel. Right? And that actually corresponds to some box on your computer screen. Yeah? So one thing I can do if I'm really sneaky is say, okay, I'm going to actually take my pixel grid and I'm going to take like every group of like 5 pixels and make kind of a coarser pixel grid, which is a bunch of 5 by 5 things. Right? And first, I'm going to rasterize my triangle there, right, and generate a bunch of fragments. And then that list of fragments tells me which ones I have to rasterize the interior of, right? Because if I turn off a fragment at that step, I know that the entire inside of that 5 by 5 box doesn't need to be rendered. Yeah? So this is another kind of trick that people use, which is called hierarchical rasterization, where you do blocks of pixels first in kind of a conservative manner, where the calculation you want to know is, does any pixel in this block intersect the triangle? And if the answer is no, then I never parallelize over the interior. So you guys see the name of the game here? These are all just like totally hacky ways to just reduce the amount of work that my GPU has to do. And the big trade-off here is parallelism versus the speed of a single thread. Okay. There's like a million references you can look at that are kind of fun. If you want like a fun retro course project, implementing these sorts of things and making like, you know, Pac-Man or something would be a pretty fun one. Getting to go efficiently is remarkably hard, especially if you aren't used to writing like low-level hardware code. Okay, any questions so far? Cool. Right. And then this is what we already mentioned. This old school rasterization technique looks something. Okay. Right. So the other thing that we have to worry about is dealing with the depth the proper way. And one thing you might notice is, for instance, what if I have a negative coordinate for all 3 points in my triangle? What do you render it? the negative z coordinate? The answer in this case is actually it's behind you, right? And similarly, when it's right at your I, when you homogenize, you divide by 0, and that leads to this idea of the view frustum. So there's a technique here, which is called clipping. Is a vocabulary word. Today's lecture is just a lot of words that you guys know the lingo that people use to talk about graphics card. This is another one that I've already used, I guess, in today's lecture, which is to say that the user, or in this software, defines what we call clipping planes. These are planes that define your view frustum. And you make a big pass over all your triangles, check if they're inside of the view frustum, and if they're not, then they're moving. Yep? Right. Okay. So there's an additional related idea here. Notice that each one of these tricks then comes with this big iceberg worth of other ways to make it even faster that are just more annoying to get right. One clever technique out there is called view frustum culling. Notice we're going to start like taking pairs of vocabulary words we've had before and like smashing them together. So remember in our ray tracing lecture, what was one of the basic techniques for accelerating our ray tracer was to put a big bounding box around the shape, and if that bounding box didn't intersect our ray, then we didn't need to check anything inside. Yeah, if you remember that, you should review before you pitch it. Right, then you can do something similar here, right? If I have this bunny and the entire bounding box of the bunny doesn't intersect the view frustum, I obviously don't need to rasterize the bunny. Yeah? So in this case, view frustum culling would help me with this guy, but I'd still rasterize this one and this one. Notice this is actually not saving me, well, it is saving me graphics card time, but it's mostly saving me time moving data back and forth to my graphics card, right? Because I can just check the box, like check the vertices of the box around the bunny here on my CPU, right, which is streaming data. It's like handing data piece by piece to my graphics card. And if this entire box was in the view frustum, which is a relatively small check, I mean, right, the bunny may have a million triangles. This is like a box with 8 corners. Yeah. Then I just don't even bother DMAing across the graphics card. Does that make sense? So this is basically all just to say that all this hierarchical rendering stuff we already talked about is relevant too in the rasterization pipeline. But typically the hierarchical stuff you can do isn't on the individual ray basis, but rather on the frustum basis. Right? You want to just see if an object intersects the frustum. If it doesn't, okay. One additional fun trick we can talk about. I would consider this to be mostly a fun trick rather than something that people actually do. I'm not totally sure that this gets implemented a lot anymore. There's an idea called homogeneous rasterization. And the basic idea here is relatively recent. 1997 is actually pretty recent for a rasterization algorithm. Is that, again, we just really don't like division in the graphics pipeline. Right? Because it just generates problems. Right? Like division by 0 is problematic. So in the homogeneous rasterization idea, we say, okay, let's say that I'm looking at a triangle, and it's through the view frustum, right? So I know the vertices of my triangle in the plane. And of course, so the way that we described it, right, is that really the interior of the triangle is like a half plane. So we can draw an additional object, which is actually a 3D plane, which goes through which has vertices which are your eye, this point, and this point, that are determined by the half space of the interior of the triangle. That makes sense? So this is now a half space in 3D. Yeah, so this is a 3D shape that extends from your eye into the real world. Okay. Right, and so this picture on the right-hand side is your triangle in 3D. But it's still the same object in the world. Yeah? Right, so the kind of clever trick in homogeneous rasterization is to treat pixels as 3D points where the z coordinate just happens to be like 1, like the position of your camera plane, and to do 3D calculations as to whether or not the interior, a point is in the interior of the triangle or not, by basically checking if it's underneath these 3D planes or not. And the reason for doing that is simply because it saves you a camera projection, which sounds really goofy, but actually is one big source of inaccuracy in the graphics pipeline. Does that make sense? And the nice thing about this trick is it works for triangles in all kinds of weird positions, whether behind your eye or what have you. And that it still just uses this incremental tricks. Okay? Right. So this removes some need for clipping because what can you do? Well, now you just check if a triangle, you want to look at the intersection between your view frustum and this new frustum which your triangle has generated, and do a little bit of 3D math. If those two things intersect, you rasterize it. Right? So that way you don't fall for my trick question right there, where you rasterize a triangle. Here, right, all three vertices of this guy were outside of the 2D image. You still need to rasterize it. In this case, you could have figured that out by looking at the intersection of the 3D frustum defined by the triangle with the frustum for your eye. Yeah? And that's really just intersecting touching each other at the end of the day. Okay. Right, so the next thing that we need to do, we've now generated all the fragments for a given triangle. Now we've got to actually decide what color they have. Yeah? And that is carried out by a piece of machinery called a pixel shader. And these are yet another thing that happens in parallel massively in your GPU. Because your graphics card has like hundreds of threads that are all going at the same time, parallelized over all the pixels in your image. Yeah? And these threads are called pixel shaders, which is not surprising because they are run to generate pixel colors. If I have n by m images, so like I have 100 by 100 image, right? So I have n squared pixels in my screen, say. How many times does my pixel shader get run? The answer is these things are completely unrelated. Do you guys know why? It's a great trick question for like midterms. Right? It would be easy to say that, oh yeah, I run pixel shader once per pixel. Remember we talked about overdraw. Yeah? So it could be the case that I generate a fragment, I do all this computation, and then I throw it away. Right? Or it could be the case that there's some pixels for which I never generate a fragment. Right? Like maybe I only render one triangle on my entire screen. Yeah? Yes?
Why would you, so you can calculate the Z, this whole Z stuff. Why can't you do that before calling it a pixel shader?
Well, there's sometimes you might want to write a shader, you might want to implement your own Z buffer. So maybe I want to take my triangle and apply normal math and perturb the positions of the Z value a little bit before I do my Z buffer check. Right? So that would be an example where I actually want to generate that fragment before I throw it away. But you're right that typically I think you wouldn't do like a really complex shading calculation until you're really confident that the pixels is. However, let's say that I'm rasterizing one triangle at a time. I don't want to have to revisit that triangle. Right? And so one thing I might do is say, okay, it's on top, like I check my Z buffer, this is the visible thing. So now I do all that shading, but now I render another triangle, and maybe that one's on top of that guy, right? And so that would be a scenario where you might do a shading computation that was useless. There are multi-pass techniques that don't do this. Yeah? And so in a multi-pass algorithm, maybe the first thing that I do is iterate over all of my triangles and just rasterize the Z buffer. And then in a second pass, I rasterize the triangles again, and as I rasterize them, if their Z buffer agrees with the value I computed in the last pass, then I render it, and otherwise I don't. Right? Those are more advanced, right? And they actually require touching your data point once, right? I have to iterate over my triangles twice. That make sense?
So how do things like glass?
How do things like glass work? That's a great question. So there are two types of glass that you see in raster images. The first one is basically tinted, non-reflective glass. Like this is what you see in video games. So in that case, it's quite simple. You would just, after you rasterize your scene with basically that window removed, then you would just do a pass where you like maybe up the blue content of the pixels inside of it. Like you just ignore the Z buffer and edit your buffer a little bit. If you want a reflective window, it's quite hard, right? Reflections are really tough in the rasterization pipeline. So typically what you would do is actually render the world from the point of view of the inside of the window in order to get those reflected rays correct. And then raster the scene again a second time, or now every time you find a point inside of the window, you look inside of this other raster image you already generated to read out the reflected color. This is tough stuff to implement. Yeah. Any other questions? It's a great question. But anyway, because of overdraw, it's unclear the relationship between the number of fragments and the number of pixels on your screen. That's the basic takeaway here. And that there are reasonable cases where you may actually do a shading calculation and have it just get thrown away, because otherwise you'd have to make multiple passes over the triangles, right? Because you need one pass to figure out what's top, and then the second pass to do the coloring, and that may itself be expensive. Yeah. You guys can see how the way of thinking is quite different in the raster world, right? Okay. So we're going to talk a little more about pixel shaders over the next couple lectures, because these are things that people will spend a lot of time playing with, right? Okay. And finally, and of course, again, I mean, you are absolutely right that depending on who implements this stuff, you might swap these two steps. You test your visibility, update your frame buffer, all that good stuff. Basic issue, of course, is figuring out which things are in front. And as we've already talked about, the Recasting algorithm is quite easy, right? Because you just generate a single ray. But notice that you actually did do extraneous computation too there, by the way. It could have been that you intersected the ray with the tree before you intersected it with the house. So in that case, you did spurious intersection, but you only did one shading. Here you might do spurious shading, but just kind of one intersection. That's a little bit too slick of a thing to say. In both cases, there's a lot of extra stuff that happened that got thrown away. Right, so in the Z buffer, essentially what you're going to rasterize is your house, but also this depth map. In the basic algorithm here, you update the Z value and the color. Yeah. So relative to the question we had before, you're absolutely right that if I fail this Z buffer check, then I don't have to call my shading code. But it could be that I pass the Z buffer check, do the shading, and now I rasterize another triangle, and he also passes the Z buffer check and goes on top. Okay, great questions. And of course, the really critical, difficult case here is this thing that I tried to draw on the board a couple weeks ago and totally failed at. Right? We have 3 sticks, and none of them is on top. Right? So there's no just like ordering of these sticks that would somehow rasterize the Z. Incidentally, there are algorithms that just ignore the Z buffer altogether. Right? If you look at computer graphics circa like 1965, 1970, they all use this algorithm. They even gave it a cute name. It's called the painter's algorithm. I think this actually gives painters a bad rap, right? Like essentially what this is saying is that a painter only knows how to draw one object at a time, and they can't deal with occlusion. I'd say, like, I'm failing to think of, for some reason I want to say Picasso, but he's actually a terrible example. I don't know, Botticelli would prove us wrong, right? That painters can deal with occlusion. But the basic idea of the painter's algorithm is I'm going to force myself to draw an entire rectangle here before drawing the next one. And notice that this scene is an example of a scene for which the painter's algorithm would fail. There is no painter's algorithm that could draw 3 rectangles and get this occlusion pattern right. However, there are graphics pipelines that might say, yeah, that's true, but if I took this rectangle and I clipped it, so I made it into 2 rectangles, now I could use the painter's algorithm. And it's kind of nice because I can parallelize in different ways. Right? So maybe I do a pre-processing step and mess with my geometry, and then I can use techniques like this. Yeah, that's probably not the case in 3D where these calculations get really complicated. But if you're doing, like, if you're engineering operating system style graphics, right? Like you're making Windows, and like Windows still needs graphics and it still needs inclusion, right? Like you can put one window on top of another, but your Z buffer is much less complicated, right? Because you're very unlikely to have like 2 windows on your computer screen that mutually include one another. I don't think that happens. So in that case, these sorts of algorithms are perfectly fine, right? Or even a lot of 2D kind of video game scroll style things. That makes sense? Any questions so far? That's, by the way, a perfectly valid use case that we should all think about, and I think we neglect in graphics a little bit. Okay, so the questions we're going to think about in our next lecture, which Ed is going to fill in, is how do you actually get the Z value? So remember the rasterization algorithm that we were talking about is pretty much 2D, right? I compute all the pixels inside of a triangle using all kinds of 2D methods, right? And one of the really tricky things that we can do is as we do these incremental algorithms that walk in the interior of a triangle and fill in the pixels, we can also do incremental algorithms to update the Z value, only using 2D math. They're just going to look like weird calculations, right? And these are valuable because 3D math is annoying. Essentially, you have 2D buffers on your computer screen. You want to make as much use of them as you can. Okay? So that's where we'll stop for today. In our next lecture, Ed is going to be here, so he'll be talking to you guys. I'm sure he'll be much more prepared and organized than I usually am. You'll have a nano quiz. Your exam is next week. You have homework due, project proposal. It's a busy week. So, with that, I'll see you guys next time. And, yeah.